I'm a little behind because of moving. I'm waiting for my internet to go at my house. Oh yeah? Oh yeah? You moved?
You know, Cox and Run the same day.
Well, that's nice for you. Right?
Just saying.
I have Cox too, but for some reason there's some issue with the wiring at the place. So what can you do? So 12.6, I rushed a lot at the end because I just really wanted to get to a point with the math. You've got to get through the math, and it's very easy to lose the idea in the math. But the idea, let's take a step back. Put this up here.
Wait, quick question.
Yeah.
Random conceptual thing. Is that XY traces taking with the level curves?
Say again.
XY traces and level curves?
So XY trace is the actual shape it has in that plane. Level curves you draw on an XY plane, but you're just pushing it all down. Like if it's equals 7, you just push that down and it might be a circle on the XY plane. Yeah, it's like a projection in a way on that plane, or level curves.
Is it the same way you cube it, or like you set z equals to whatever? You just set the thing
Yes,
to
exactly.
0, same way.
Exactly.
It's
You
just
said
a-
z equal to something. If I wanted you to draw a contour curve, what's the only difference there? Yeah, I have to give, that's what I'm going to do on the test. I'm going to give you a shape. I'm going to actually ask you to draw the traces on top of the shape. And then draw some contour curves on top of the shape. Alright, so they're just the level curves where they're supposed to be.
So
That's what contour curves are.
So you're going to give us kind of side view and kind of draw those?
Yes. I'm going to give you a view where it's actually able to, I'm not going to give you this shape and have you looking from the top. No, it's not good yet.
Paint by numbers, key to go with it.
What's that?
Paint by numbers, key to go with it.
Numbers?
Paint by numbers.
Oh, yeah. All right, let me see. I want to take a step back here real quick if I can. To partials. No, I don't want that. Go away. Yeah, here we go. Now, this idea is pretty simple, especially compared to later ideas. But I really want to make sure you guys understand this idea. The reason that partial derivatives were really easy is because, what is this black line here?
Part of it. That's just a curve, it's a level curve.
And those are the outputs specifically that come from what inputs? What are we doing here in this case? We're holding y at b, so we're looking at fx, right? We're looking at fx. You guys with me? Because what does fx do? You let x change and you see what it's doing, but you keep y the same. So it's really just taking that cross section. Because if I have this three-dimensional figure, what's one way I can do it? Well, let's look at this cross section and then this cross section and so forth.
So the z x or x z trace?
Not really a trace, but it's sort of related. It's parallel to the xz axis. Sure.
I thought it was a z.
Yeah. Could you call it an AB trace, seeing how it's AB f of A?
Let's not get too deep. This is just the point, though, right? You can't really call it an AB anything.
Yeah.
So the point I'm trying to make, and let me see if you guys remember from last time. We did some work and we got to the point this here. That equation is this black line in general. This black line is easy because I'm holding y constant and I'm going along a line that is parallel to the x-axis, right? You guys with me? So in this case, my u has only one component. My u only has the I hat component. It's only going parallel to the x-axis. And to generalize that, I need both of these stupid things to be active. Right? So if you just turn this, don't hold y or x constant, but hold them to follow a certain line. And then the cross section you cut out, that's the general directional derivative. So another name for fx is the directional derivative at any point in the I hat direction. Good God. So I'd rather call it fx. But in general, I could be pointing in any direction, but it's the same idea. This function is specifically the outputs from some line that u defines the direction of. So in this case, we're following the line y equals b, right? And the outputs that come from that, y equals b, the outputs that come from that. And in this case, we're following some general line that I've got to define using I hat and j hat kind of things, components of the u, components of the direction that I want to follow. Okay, maybe. Because some of you guys that stayed after, I said this was one of the key ideas that's really easy to overlook when you're reading that section. You kind of skim through the math, you're like, get to the point, right? I mean, that's what I did as a math student, I'll be honest. Very often I'm like, what do I do to do this problem? Where is it? There it is. That's the equation to do this problem. Later I started to appreciate, oh shit, I gotta understand all this stuff now that I'm in a higher freaking math class. What is all this other stuff that came before it? So there's that guy. And now, all I want to do now is take the derivative in one dimension now. So that's what fx does very directly. It takes the derivative with respect to x alone in one dimension. One direction. This is still one direction. In fact, how many true variables are up here? Inside here, how many true variables are there? One. They're both dependent on s, aren't they? A and B, U1 and U2, those are all constants. You with me? U is a given directional vector. Those are constants. U1, U2. A and B is the point that I'm standing at, right? U just tells me which way to face. So this is still one-dimensional. It's just not an x direction, not a y direction, some composition of both directions, of course, to be more general. Whew. So, if I remember correctly, I think we got, and what I would do if I were you, is I would obviously go back and read through that part of the book. And what I'm hoping is, even if I didn't make much sense up here, you caught some of what I said to help you interpret what the hell they're saying in there. Right? Because this is important to know why this works. The really bottom line funny thing is, the result is so damn nice and easy. It's exactly what we expected, that it's really easy to overlook all the work that went into getting there. Right? I think we got to this point here. So again, S would be sort of like my H. S is sort of like my H. So let me come back to 12.6 now. They don't give me a nice picture. Oh, too bad for me.
Directional derivative along the facing A.
There we go. This is actually good. So just like this H here, S now acts as my H. It tells me how far apart this point is from this. So I'm at some point AB. I want to know the derivative in this direction, right? So then I go that direction for a little bit and get to a point, and then I find the slope there. What do I then do? Let those points get closer and closer. That sounds very familiar. Until the distance between them approaches 0. So if I do this, if I take this derivative and plug a 0 in, that is the derivative I want. That will be the derivative at that point. Okay. So all I have to do now is figure out what the hell that is. So if we look at GS, is that, what would G prime of S be? So let me write GS a little bit quicker here. Like that, where XS, A plus SU1, YS, B plus SU2. So now we know how to do these derivatives, don't we?
Partial of
Yeah? Partial of F.
partial of
Good.
then
DX. DS.
Partial
then
partial y.
partial
dy ds.
over T.
dy ds, right? What is dx ds? And I think this is one of the last things I did. What is dx ds? Do that for a second. What is that?
A plus what?
Dx ds would just be
U1.
u1,
Yeah.
right?
Because A would vanish.
And what's dy ds, incredibly enough?
U2.
u2. Oh. And what's df dx? Just give that a name. Partial derivative with respect to x, we call that, what do we call that? Shorthand. We probably call it fx. And probably enough fy. So to be more specific, this will be fx at AB u1 plus fy at AB u2 when I evaluate this at 0. Because at 0, what point am I at? AB. Cool. When s is 0, I'm at the point AB. So at 0, that's the derivative I want. That brings me back to the AB point. That's where I'm actually standing. I don't want this other point. That's what algebra says I need. I need 2 points. Calculus says, screw you, algebra. I just need 1 freaking point. Let me make that come really close. And now I'm pointing in the right direction. So let it go to 0, just like we let h go to 0. This is a really cool way to do it, though, because I don't have that ugly-ass limit that we had last time. There's no limits involved here. Because I've taken my function down to a differentiable piece that gives me what I need just by taking its derivative. I don't need a limit definition anymore. We know derivatives, damn. So this is my directional derivative at u of f. I mean, at AB of f in the direction of u. Good God. Yes, it takes that long to say. It's too bad. Because you got to be standing at some point, facing in some direction. So you got to say both those things. So let's do something concrete. Let's actually do a problem.
Professor?
Yes.
And those f of x and that f of y on that last equation you wrote, those are the partial? Or those are the partials?
Yeah, this is the
Yeah.
partial,
Yeah.
the partial, yeah. Cool. So let's see. Here we go. Let's do this example. Find UF AB in the direction U equal to So real quick little note. I do not want you to freak out. A part of this course and a part of any higher math course is to realize when you're facing lower level mathematics where you should not make a mistake. So if I asked you, what the hell does this mean? Could you give me an angle in which what direction am I facing? You could draw yourself a little xy. 1/2, negative root 3 over 2. You got a little triangle going on. You can figure out that angle there, right? This will be 1/2. This will be square root of 3 over 2. So the sine is bigger. Anyone know what reference angle that is? What that angle is? So sine has got to be larger. So it's got to be 60, yeah, 60 degrees. Pi over 3, 11. Cool. You didn't quite see what I said. You guys agree this makes this triangle here 1/2 root 3 over 2. That's negative, so it's pointing down. This angle with respect to the x-axis. Just in case you see a problem that says you're facing in a direction 30 degrees below the x-axis, or 45 degrees above the x-axis, something like that. That shouldn't freak you out. You just look at the unit circle and give yourself the coordinates that you need. What's got to be true about this u vector that I use?
Unit vector.
It's got to be unit vector. So if they give you the vector 3, 4, shit. You got to take a second and figure out its length, which is easy. Nice Pythagorean triple. Divide by it. Make it a true unit vector. You cannot throw it into the directional derivative formula unless it's a true unit vector. Okay. So, first question is, what is f? just all that stuff, or even don't make too big of a deal out of it. Just like f of x just took the place of y, f of xy just takes the place of z. So f of xy is 1/4 x squared plus 2y squared plus 2. So figure out what's fx and what's fy.
Just 1/2 x.
Yeah, so fx is going to be 2x, 1/4 to 2, 1/2 x. And of course, everything else goes away.
Fy is just y.
Good, because that'll come down 4, 1/4 to 4 is 1, so you get fy is y. Are we doing so far? Now, obviously, this one is a decently easy one, because fx happens to only depend on x. Does that always have to happen? I've got to be very careful with my examples, because people generalize the wrong things. This could be, I could have stuck in a y right there, and this would have had a y in it, right? So don't think that it's always a force.
Can this one be on the test?
Not anymore. I could put one like it on there. In order to do the formula for this, right, the formula for this is fx at AB u1 plus fy AB u2.
And those u's are vector, unit vector u's.
Those u's, be careful, they're parts of the unit vector.
So they're just vectors right there.
They're the components of the vector, exactly. So in this case, what's my u1 in this case?
You want
1/2,
1/2.
right? So u1 is 1/2. What's f of x at AB? So what's 1/2 x at 2, 2? Everybody see where I got that? What's AB? What's the point of AB? 2, 2. And of course that 5 is what?
Z.
The z output. But when you're talking about the gradient, it only cares about your domain, which way you're facing in your domain. You with me? Sort of. That's the piece I keep trying to make a big deal out of, and now you start to see why. Very often we only talk about the domain. We're two-dimensional. You got to remember there's a third dimension that's over us all the time, or under us, or wherever the hell it is, the output. So the point is 2, 2 because they gave that to me. Mighty nice of them. Me. So at 2, 2, what is fx? 1/2 of 2. So that's 1. And what's fy? 2. 11. And what's u2? Yeah, negative √3/2. And by the way, I didn't really say this, but obviously this is a unit vector. It's right off the unit circle, so you don't have to do anything. So what do you get for the directional derivative in that direction at that point?
1/2 plus 1/3.
Yeah, 1/2 plus, so 1/2 minus √3, and whatever the hell that is. Sweet. Yes.
So this equation applies only for the three-dimensional functions. If we have more, does it apply or no?
The way that we've done the math for this, it only applies for that, but you can extend the math easily. We're not going to, but you could extend it.
So
Because really this directional derivative, a better way to write this, because you can imagine just tacking on a u3 there, right? Yeah. We don't often directly deal with four-dimensional surfaces in this class. You with me? We will, actually, we will. Very often it'll be indirectly. Like we'll deal with this domain. What's the domain of a four-dimensional object most likely going to be? Three-dimensional. So we can draw the domain of a three-dimensional object, a four-dimensional object. We can draw that domain because it's three-dimensional. We can at least give it a try. It's at least possible, right? But that's a good point. You can extend the math here because really what this is in more general terms, and I think I said this last time, is like fx, fy at AB dotted with u. It's just a dot product. So couldn't you have an fx, fy of z dotted with a three-dimensional unit vector? Certainly, yeah. We don't, math is extended. Okay. Yeah.
I'm just curious what the number would actually equate to in this.
So what this means is exactly what it normally means. If I'm standing, this would maybe be on this side, because it comes out negative, right? Negative 1 point something or other. So that means if I move, if I move in this direction, right, it's a little bit more than that. So we figured out it was a 60-degree angle here, right? If I move in that direction, my outputs are going to go down by about how much for every step I take from that point? About that much. So the derivative means exactly what it's always meant. It tells you how much your output changes as you change your input. The weird thing about our inputs are they are two-dimensional now. So that's why limits are freakier. We've got all these different paths you can take in our two-dimensional input range. Input range, I like that. Derivatives are freakier because you got to identify a direction you want to face in to even know what your derivative is going to be. We didn't have to do that before, right?
So it's the slope of the tangent line at that point?
Good. Another way to look at it, actually try to extend it from 2 to 3 dimensions. In 2 dimensions, you get a tangent line. In 3, we probably get a tangent plane, which would be section 12.7.
So the slope of the tangent plane.
I like, well, in a way, it could be used to find a tangent plane. Yeah. How are we doing so far? Decent? Semi-decent? Yes.
So that is how the output is changing, that is the rate of change, the outputs?
That's the rate of change of the output in this direction from that point.
Okay.
Cool. I mean, from that point piece is nothing new to us. The in that direction piece is new to us, right? We know that you have to specify where I am, because on a parabola, if I'm back here, it's negative. I'm over there, it's positive. You got to tell me what point I'm at so I know what the derivative is. We never had to have a face a certain direction to be able to discuss a derivative. Now we have to. I keep almost making a point. Oh yeah. If this came out to be 0, that's an interesting situation. And I think I've already said this, but who can remember or who can figure out what does that mean about the direction that I'm moving in? What's special about that? On one level, of course, what's happening? My directional derivative comes out to be 0. What's not happening? Yeah, my z is not changing, which means I must be walking in the same direction as a level curve. You with me? Because level curves are defined to be where z is a constant, right? So that's interesting. Okay. One little thing. Let's take a step back here. Let's write this even better. Let me focus on the part of this that's really, really, really important. Can't I write this like this if I really felt like it? No. Actually, I should be a little more. Yeah. And this would be if I really want to screw it. It's just you. This piece here by itself really, really gets at what we were talking about earlier. It's sort of the total derivative in a way. This is what's known as the gradient. You can spell it. I have created a new letter, which is the A and the D together. Okay. Sorry. So that's called the gradient. This is the symbol for the gradient. It's an upside down.
Delta.
Yes. Cool. That is incredibly important. That is the piece of this. And I think at the very beginning I told you, we're going to be doing a lot of work to get this directional derivative. Once you leave this section or this class, the important thing is going to be this piece, this gradient. So just to calculate the gradient by itself, I don't want to make A and a D together for some reason. If I had a function the gradient of this function can you guys do that? Go ahead and do that. Just Just make a vector out of it, right? So realize that the gradient is a vector itself. So a really good question, you can do the work, it's just derivatives. The next question would be, what's special about the direction it points? A vector points in a certain direction, doesn't it? So the gradient itself is a vector, it must be pointing in a point at some specific point, right? It must be pointing in a direction. Let's see now.
Eight X Y cubed.
Yeah, so this will be
8xy cubed. Oh.
Y cosine,
Cosine, or y cosine,
X,
X1,
Y.
X1.
and 12 x
12.
squared,
Y
y
squared.
squared, minus x cosine,
Yep.
cosine x.
Okay, cool. So that's nifty. Now if I gave you a point, so this could be like part one of a problem. Part two would be, okay, what's the gradient at the point, I don't know,
Give us a 0.
1,
0.
Square root of 40.
Pi.
yeah, let's do like a 1, I don't want pi in there.
0, 0, 0, 0.
1, 0 is fine. Yeah, 1 after A and B. So this first piece is easy.
0.
0. So the point 1, 0, it's not pointing in the x direction at all.
And the next one
Y.
is just 1.
In the next one, so this piece is 0 I hat, because that's 0 of course. Y is 0. Here y is 0 again. Yeah. Over here I get
0.
0
Minus 1.
minus,
1.
yeah, 1 times cosine of 0 is 1.
Negative.
Negative j hat. So you get negative j hat. Nifty. Now what that direction means. Now obviously, at a point, the gradient has a direction. If I dot that with some vector u, then I get a directional derivative. And do you see how that's a dot product? What will always do to a vector if you dot it with a unit vector? Let me say this again, because this is important in general. If you have a vector and you dot it with a unit vector, what will always be true about the output related to the, how does it relate to the original vector itself?
It will be the same length as the original
It'll be the
vector.
original vector.
If you dot it with a unit vector, the dot product, of course, depends on the relative directions, doesn't it? If that unit vector you dot it with is at a 90-degree angle, it'll be 0, right? Which is interesting. But more generally, the gradient by itself is the biggest it could be. The minute I dot it with something, it's smaller unless that vector is how related to the gradient? Parallel, I love it. So think about it. It's all based on a dot product. You go from a gradient to directional derivative. So if I'm facing in the same direction that my gradient points, then am I not going to have the largest output for my directional derivative? So what is that? So, let me make sure everybody's with me. So if I'm facing, if my u vector, the direction I'm looking, is the same as the direction my gradient would be pointing at that point, I'm going to have the largest possible output. Cool? Okay, good. I just want to say that again, just to make sure everybody's with me. What does that mean then about the gradient vector itself? It points in the direction of what?
The steepest slope.
The steepest descent. The direction, that's actually straight, but the gradient points in the direction that your derivative, that your outputs are growing the quickest. You with me?
That's what the gradient does?
Yes, the gradient points in the direction of steepest ascent. Which means, and I always like to think physically, if I'm on a mountain, if I'm on this side, if I'm looking this way, it's going to be 0. And maybe I'm going to walk around the mountain. But if I turn this way, oh shit, and I'm going to go straight up this freaking mountain, my gradient is going to point in that direction. and I dot product it. If I want to face some other direction, I take the dot product and see what it is in that direction. You guys kind of with me here a little bit? It sounds very important because I went really slow and I normally talk really fast. The gradient points in the direction of steepest descent. So the negative gradient, so just take the negative of the gradient that points in the direction of steepest descent. If you want to get the hell back down the mountain.
Professor?
Yeah.
For your first equation, that is actually the gradient. I thought you have to dot it with a u vector too.
No, this is the gradient. The gradient is used in the equation to get the directional derivative. I dot product the gradient with some direction I'm facing
Okay.
to see how steep it is in that direction.
Okay, so the u vector is not part of the gradient.
No, definitely not. So this piece here
That's the gradient.
is the gradient.
Okay.
If I dot it with some directional
Directional
piece,
derivative.
it'll show me what part of that gradient is in that direction, what part of that derivative is in that direction. So let's take a little break. Oh, go ahead, sorry.
So right there in negative j, it's straight down.
So what this is telling me is I want to, now be careful, that's straight down in my x, y. So it tells me if I'm standing at the point, what was my point? 1, 0. If I'm standing at the point 1, 0, which way should I go to have my z grow the quickest? This way. I like it. So my outputs, maybe it's here, and then it goes up here if I move in that direction. Yeah.
And by grow, you do mean the greatest increase as in positive z?
Exactly. The biggest increase. So it could be negative z, but it's gotten less negative. So it increases. It's the biggest increase. So the gradient points in the direction that would result in the greatest increase in your outputs.
So it doesn't actually give,
The slope.
it doesn't actually give us slope, it doesn't
Not by
actually
itself, of
give us
course.
any tangible information. It just says, hey, if you pull in a direction that is pointed straight down, you'll have the maximum.
Exactly. If
rate.
you dot it with itself, you actually end up with the derivative in that direction.
So the gradient itself is not really graphable.
No. Well, it is. You can represent. I just did.
Okay.
I can represent the vector, but it doesn't by itself mean a derivative yet. It's not a derivative yet.
Okay.
But it's useful, obviously. You do a lot of physics with it. If any of you guys have ever heard of Maxwell's equations, anybody ever heard of Maxwell's equations? Okay, look it up. You'll see that symbol in every equation, and those are the 4 equations that govern electromagnetism. Maxwell's equations. You have a lot of shirts that have Maxwell's equations on them. One of them I love. It says, "And God said," Maxwell's equations. It's like, sweet. All right, so let's take a break. Come back a little bit before 2,
At Python?
just to be vague. Yes, come back at pi time.
So, Professor, that gradient of negative j hat, that's straight up and down, or I'm sorry, down 1. And
So if this is my x and my y, and I'm at the point 1, 0, where do I move so that my above me it gets higher? I move that way. If I move in some other direction, it's not going to get higher as fast. If I want it to increase the fastest, I move that way. Maybe. So in that case, you're standing in the mountain. You're standing right here. Which way do you want to go up the fastest? That way. So in the xy plane, it would relate to this direction, right? So you always have the output, what's happening, and you have the direction you're actually changing your inputs in. Okay, good. Because the hardest part about this section of the class is you've got domain and you've got the surface itself, the outputs. Some of the math we do directly on this, but there's always this in the background, right?
So it's like expectation where you will find the maximum and minimum of the function.
yeah, it sounds like a maximum.
We're heading in that direction. Obviously, to be able to do maximum problems, we have to have a hard defined derivative, right? And we've got basically that idea with the directional derivative. The gradient might help us do some of these problems quickly.
I was curious how the gradient would work if, say, you were at the bottom of a paraboloid or something like that.
What do you think it would be then? Which direction should you move?
Just in the z, not at x or y, just straight up.
So if you're at the top, if you're at the very top, the very peak of something, which direction should you move to go higher?
Should.
You should, right? In which direction should you move to go lower?
Any
Any direction. So what do you think, how do you think the gradient's gonna come out in that case? Yeah. And we could try it out. We could actually do, what was that equation from the quiz here? Because you guys, basically, if you did the quiz correctly, you proved, let's just do this one here.
And the gradient is written as triangle F. Is that what you were doing, Professor?
Okay, sir. So at the point 0, 0, 0, I would be at the minimum of this, correct? In fact, you kind of proved that by showing the XY trace, it's just that point, and it goes up from there. So the gradient at that point, let's see, because you're thinking it's going to be a little weird at that point, right? I won't say schizophrenic, and that's the misunderstanding of schizophrenia, but it's going to have multiple personalities at this point. So what would the gradient of this function be in general?
Oh,
Yeah, I mean, right, the whole way is better.
Now fill it in.
Yeah, 1/4
X.
Yeah, so when you, with respect to x, this piece goes away. Then you get 1/4 x
Plus Y.
plus 1.
plus y, I like that. Right? So what's the gradient of that at the point 0, 0? Yeah. So that's the one vector that means go nowhere and go everywhere, right? Because if you're at the bottom already, I want to go any direction to go up. The only way I can show that mathematically is to get the 0 vector, because that means go every freaking direction to go up. Because you're alright, you hit bottom, dude. You can only go up. Which way do I go to go down? No direction. Again, 0 vector means don't go anywhere. So the 0 vector being so ambiguous is incredibly useful. Mathematically, I'm going to get 0 here for the gradient. How do I interpret that? 2 ways, because I'm allowed to. It's ambiguous. It means all directions and it means no direction. That's why I made that point. I can't remember, I think the book is specific about which one it means, but it actually means freaking both.
So it would be like a perfect ball or sphere balanced on top of that hill. It's which way do you go to go down? Well, if it's perfect, it's not going to move. But
Oh, I see what you mean. Yeah. That's getting more like chaos theory. Right?
oh,
It sounds more like that Jeff Goldblum
yeah,
scene from
Jurassic
Jurassic Park.
Park.
Yeah.
This here, what do
Which
you
is
do?
less mathematical and more fluid.
Yeah.
Philosophical.
Butterfly flaps its wings and Peking it's sunny and it rains instead of sunshine.
We gotta kill that butterfly.
Yeah.
What's it doing? It's wreaking havoc over the whole Earth.
Do they make you do that as a math major? Chaos?
Well, it depends on if you want to. I mean, I took a course that involved chaos theory in it, but I didn't get that deep into it, to be honest. We did some physics stuff with it because the motion of pendulums, we made this pendulum that had a pendulum in it, so we got to machine stuff, which is always interesting for physics theorists to go in and actually do something,
Right.
you know, well, motion.
Yeah.
But we made a pendulum that actually had a little cutout in the middle and had its own pendulum in the middle. So it has all these ways it could rotate. So we started it off as best we could at the same position. We videotaped its motion after that. And we showed that we basically never got the same motion after, which is chaos theory. I mean, you can never start it exactly. You can never have the temperature exactly the way it was. The air drafts exactly the way they were. The whatever, exactly the way it was. You can't. So many variables. You start it where you think it was, and then it does entirely different motions. That was kind of cool. A little bit beyond what we need to do here.
That's why it's break time, right?
Yeah, exactly. Talk about whatever I want to.